All right, hello and good morning. Our second set of notes dealing with atomic structure and periodicity deals with shielding and such, because I couldn't think of another name, so I went with that. Why not? So, first thing, getting into shielding in a multi-electron system. So obviously this will not work for hydrogen. We know that electrons are attracted to the nucleus and repelled by each other. That's just a normal thing in all atoms because they all have protons and they all have electrons. Again, this does only work for multi-electron systems, so hydrogen fails spectacularly in that sense. So basically, the outer electrons, we know the name for those things, valence, they are shielded from the nucleus by the core electrons. Now, this is not completely shielded, or that would suggest they go flying off the atom, which we know doesn't happen. It's just there's a diminished effect. So we have the shielding effect, and outer electrons do not effectively screen each other. So ultimately, we're looking at the core electrons that are the shield. All electrons that are in the same outer energy level, they don't really shield each other in the same sense of the word that is shielding. So the shielding, as we kind of said earlier, is a diminished effect. Those outer electrons, valence, do not feel the full strength of the force. No, I'm kidding. But the full strength of the nuclear charge, or actually the nuclear force, if you will. Which brings us to effective nuclear charge, otherwise known as Z effective. The effective nuclear charge is just the net positive charge that is attracting a particular electron. Now, for our purposes, we are going to deal with whole numbers. Always dealing with whole numbers. In the real world, i.e. college and after that, effective nuclear charge ends up being a decimal number, and it ends up being very different for individual electrons. Again, for us, we are only focusing on the effect on valence, and it's going to be a whole number only. Z is a nuclear charge, also known as the number of the number of protons, wow, and S is the number of electrons in the lower energy levels. So another way of looking at S, it's equal to the number of electrons in the noble gas plus any D's, if necessary, that come prior to the element you are focusing on. So again, S is the number of electrons plus any D electrons from the noble gas prior to the element you are focusing on. Electrons that are in the same energy level contribute to screening in the sense of they're all valence, but they're not included in the overall calculation because they're in the same energy level. They're in the valence shell. They do a pretty poor job at shielding other electrons in the valence shell. That's why S corresponds to core electrons. We know that S electrons shield better than P, which shield better than D, and they shield better than F. So S and P do the best shielding. D and F, they do contribute, but not to the extent compared to S and P. When we figure out our Z effective, it's just Z minus S, number of protons minus number of core electrons, gives you your overall Z effective. Again, for us, is a whole number, always. All right, so looking at the left diagram, we can see that the nucleus has a 3 plus charge, and there are 3 electrons. The 2 electrons that are within the little blue shaded area, they're in a core electron energy level and orbital. the one electron that's way out there with the little arrow on it, this guy, he is being shielded from the nucleus by those other two electrons. So that outermost electron only feels a +1, whereas the other two electrons, they feel a full +3 in their attraction. On the right-hand side, gives us this idea of penetration, which we'll talk about here coming up, where the outer electrons, they have the ability to kind of get really close to the nucleus, and then they go back to where they originally are. They're not getting or existing in the same orbital as the other two electrons, because we know, according to Pauli exclusion principle, only two electrons may exist per orbital, but of opposite spin. But we can show, which we will graphically, that some of these outer orbital energy levels do have some probability of getting closer to the nucleus. So every once in a while, those outermost electrons, they feel the full force of the nucleus, but for the most part, they do hang out in their valence shell, and they only feel the diminished effect. Any questions so far? Okay. So again, showing us the left image as last time, just giving us our calculation. We have a net +3. We have 2 core electrons. Therefore, it's a +1 charge. So ultimately, these lovely orbital things that don't exactly exist, they're just mathematical functions, help us determine the probability of finding an electron. So this here, the probability diagram for the s orbital in the first energy level, so 1s. You can see in the image to the left, the pink, it's very, very dense. It's very, very bright near the very center. But as you go radially outward in any direction, you can see that the intensity decreases. The graph on the right showing the same thing. If 0, 0 on the graph is the nucleus, then the 1s electron is going to have a very high probability closer to the nucleus. And it's going to have a very low probability as it gets further and further from the nucleus. Questions on this diagram? All right. We know that orbital shapes are ultimately defined with their mathematical function to basically contain 90% of the total electron probability. Everything here is probability. Nothing is absolute. So the 1s electrons have a very high 90% probability of being pretty close to the nucleus. Our sizes of s, we've mentioned in the past that when you go from 1s to 2s to 3s, it's like the 1s is a golf ball, the 2s is a tennis ball, the 3s is a softball, then 4 could be a soccer ball, 5 could be a basketball, 6 could be a beach ball, and 7 could be a hot air balloon, just for sake. Why not? Obviously, there's spheres. The s orbital is spherical shape, as you can see with 1s. But then you get these areas of black that you can see in the 2s and the 3s diagram that are nodes, areas of very low probability. Now, these spheres, they're not really thin. They have some thickness to them, and obviously everything in between. But when you go from 1s to 2s to 3s and so forth, there are areas that have low probability, not zero probability. It's approaching zero, but it never actually gets to zero probability. As we said, forgot to hit the button, nodes are regions of low probability within an orbital. So the 1s has no node, but when you get from 2s, the 1s space fits inside the 2s space, and there is an area where, again, low probability. Another way of looking at it, top diagram giving us, from electron cloud kind of perspective, but then in B image on the top right, we can see, as it says, a contour probability, whereas The nodes are it's a small space between 1s and 2s, but notice when you get to 3s, the size of the orbital is getting bigger and bigger. So that node space is going to kind of become larger as you go. But notice the shapes of these orbitals, they're not just thin lines like the surface only. They have some thickness to them in their area to show probability. Now, the bottom diagram, this is where the whole penetration idea comes from. We can see the purple 1s right here has very, very high probability really close to the nucleus. But then when the 2s comes along, 2s should be further from the nucleus. But then notice it has a little bit of probability pretty close to the nucleus. And then we get to the 3s. Again, higher probability further away. It's a bigger orbital. But again, notice following the graph that the 3s has some area or some high probability in the 2s region. And again, the 3s orbital also has some ability or probability closer to the nucleus. So s and p orbitals, you kind of get this idea graphically of this idea of penetration, where electrons that are in those outer energy levels do also spend some of their time, we don't care how long, but some of it, closer to the nucleus. Questions on this so far? Okay. All right, so continuing with our penetration and shielding, as we're talking about this lovely graph, it's a function. This one is showing the 2s orbital and 2p orbital over to the right. And you can see that the 2s orbital has greater or higher probability closer to the nucleus than the 2p. Now, the height of the 2p is higher probability closer compared to that main 2s. But 2s also has probability really close to the nucleus. So s's ultimately have greater penetration and shielding, for that matter, than p does, because it has two humps in the graph, if you will. So here we are, the weaker penetration of the 2p sublevel. Those electrons experience, more of a repulsive force compared to the s electrons. They are more shielded from the attractive force of the nucleus. So p electrons cannot get as close to the nucleus as s electrons, but we can see here in the graph that both s and p do have some high probability rather close to the nucleus. Because the s has a better ability to penetrate closer to the nucleus, those electrons are going to experience greater attractive force. They're not shielded as well or as effectively. They're held on that much tighter. Questions on this? Okay. So ultimately, the idea of electrons penetrating deeper into an atom, closer the electron is to the nucleus, the more attraction it experiences. It's held tighter. So the better an outer electron can penetrate through electron cloud, the more attraction it will have to the nucleus. Even though we're talking about valence electrons, and the z effective for all those valence electrons is a whole number, and it's the same in our purposes, any s and p electrons that have the ability every once in a while to get closer to the nucleus, they're going to feel that much more of an attractive force over time. Which brings us to the degree of penetration related to the distribution function. Those functions I've shown you with the graphs. Ultimately just comes down to how much probability, or what is the probability as you get closer to the nucleus, depending on what orbital you're in. So another example, here's a 3s orbital. The most probable distance is the furthest one away, compared to the other two, but we can see on this diagram, or in this diagram, that the 3s electrons do have some probability closer to the nucleus. They spend 90% of their time, if not maybe more, at the 3s orbital distance from the nucleus. But again, they can, and they do, travel closer for a little bit, and then they go back. Remember, electrons are bees around a beehive, moving around crazy. So the question, what parts of the diagram correspond to nodes or regions of zero probability? Well, yep, any part of the purple line that touches the x-axis is your nodes of zero probability, or near zero probability. Questions on this? Okay. Here's another one. Now we bring in the d orbitals. And if we look at all three orbitals in the third energy level, S, P, and D, S and P electrons do hang out further away than the D electrons. D electrons seem to be closer to the nucleus. That's why D electrons are included in your calculation of Z effective. They are core electrons only. But if you notice the blue and the black line for the 3s and 3p, they have another probability closer to the nucleus. And you look closely, the s electron has a third probability to be closer to the nucleus. The 3p does not. So the point we're getting at the end of the day, S and P electrons are very good shielding, or have good shielding to other valence electrons. D electrons, they do contribute to shielding overall, but if you're comparing S and P to D, D are much less in their shielding, because as you can see here, the d electrons have only one area of probability, where the s and p have multiple areas of probability of finding an electron to behave as a shield. Questions on this? Okay. Another graph, kind of the same idea. The y-axis kind of got cut off there. Atomic units, not sure what that is, but whatever. Now it's interesting in this one, as in we're dealing with 4p, 2p, so all the p orbitals, and then the d. Again, those p orbitals have very high probability of finding an electron compared to the d's, where you're most likely to find them. Why does the 4p and the 3p seem to go negative the further you get out, in the sense? Well, they're not likely to go there. So don't worry about this whole negative idea, but we're just showing you that the p orbitals do have a higher probability of getting closer to the nucleus than do the d orbitals. Any questions? Okay, and we are done.